Okay, so let us now solve for the shear diagram of this particular beam. So in a shear diagram, it is basically the diagram of the internal shear forces acting on the beam. So with that, guys, so suppose that this, let's say, is our diagram. Suppose that we will be drawing a diagram. Let's say that, for example, that this is now the diagram. Just for example. So suppose that this here is the diagram, meaning that at this particular point, meaning that it is experiencing this amount of shear. So at this particular point, it is experiencing this amount of shear. And at this particular point in the beam, it is not experiencing any shear as with this part of the beam. Okay. So again, this is just an assumption. I wouldn't want to assume. Let us just solve for it. So I would be erasing everything first. So in order for us to know, or in order for us to solve for the shear diagram, we would now be going from point to point, from left to right. Okay. So again, we will be solving for the shear force acting at this point, going towards the right. Okay. So let us first get the shear at this point. So again, suppose that we are to get the shear at this particular point. Once again, let me just zoom in. So there. Okay. So I think PowerPoint does not allow me to zoom in and use the power pointer. Anyway, so at this particular point, as you can see that the beam is experiencing 32.111 kilonewtons. So when we say shear, that is the force that is parallel with the cross-sectional area. So what does that mean? Suppose that, let's say, this here is our beam. So let's say that this is our beam. So when you say cross-sectional area, it is this particular area. So since our force of 32.11 here is acting vertically upwards, it is parallel with this cross-sectional area, meaning that this is the shear force. Okay? So with that, guys, at that particular portion, it is actually experiencing 32.11 kilonewtons. So with that said, at this portion, guys, we have here 32.111 kilonewtons. Okay, so how do we plot for the next ones? So suppose that you're using computer software such as fixed using finite element method for computer softwares. What it does is that it would solve for each of the elements, so point per point. So maybe from if x is equal to 0.1, 0.0001, 0.002, and the like, it would solve for it and it would plot it automatically. But then again, our job for as civil engineering students or engineering students in general, we must first know how we would be solving for it point per point. So suppose, guys, that I will be cutting a section at this particular point. Okay, so let's say that this is section A, and from that, guys, for section A, so let's say that it is now cut in this manner. So if you can remember from method of sections that if you would be cutting anything by a cutting plane, the internal force would now come out. So with that, guys, we would now be having an internal force here, or the internal shear, and we also have the internal moment. Okay, so with that, guys, you would now be solving for this shear force and shear moments. And how? So in order for you to solve for them, you would now be making use of the static equilibrium equations, such as summation force is vertical and summation moment, in order for you to solve for it. Okay? And guys, just as a shortcut, instead of you solving for these internal forces, I would rather lecture it this way. So just get the summation of forces vertical for the shear, and whatever the answer is here, that is now the internal force that is being acted upon here. Okay, so let me just write them manually. So suppose, guys, that this here is a distance x from this point. So solving for the summation of forces vertical is equal to 0, and I will say that this is upwards positive. So we have here a 32.111 kilonewton force, which is positive. Then what is now the resultant of this rectangular section? That is, so minus 10 times, so what is this distance? That is x, so 10 times x. Then, what else do we have here? So we also have an internal force here that is minus, let us say that that is now VA, for example. So from that, minus VA is equal to 0. So from that, VA is now equal to 32.111 kilonewtons minus 10x. Okay, so as you can see, guys, that this is now our equation. So from that, what I meant earlier was that instead of you writing it this way, just do it this way. So just get the summation of forces vertical, and whatever your answer is here, that is now your VA. Just like what I have written a while ago. So suppose, guys, if x is equal to, let's say, 1 meter. So for example, that this here is 1 meter. So getting the summation of forces vertical, so that is now 32.1111 kilonewtons. Or sorry, let me just write it here. So summation of forces vertical, that is equal to VA, and that is equal to 32.1111 kilonewtons minus, so this is downwards, so minus 10 times, what is this distance once again? That is 1 meter, so 10 times 1. And from that, guys, 32.1111 times 10 raised to 1, so looking at the calculator, so 32.1111 minus 10 times 1. So the answer here is 22.2. Or, sorry, 22.1. So meaning, guys, at this particular location, at x is equal to 1 meter, so suppose that this is 1 meter, just for example, or maybe this one here. If that is 1 meter, the answer here at this point is 22.111 kilonewtons. And as you can see, it has already varied. So if you would be moving further, it would now reduce up until this particular point. So since this is a rectangular section, the shear here would now vary linearly. So ibig sabihin straight line lang siya, diagonal nga lang. Okay? So again, it would now vary. So with that, guys, instead of you solving for them one by one, it would actually be better for you to just solve for whatever shear is here. So solve for the shear here, then suppose that you have already solved for the shear at this particular portion. So suppose that it is here at this point. You know that for this particular span, it only varies linearly. So just draw a straight line. So I'm sorry, I'm actually bad at drawing. Okay, so again, so what I would be doing, or what we would be doing here, is that we would be solving for the shear force at this portion. Okay, so suppose that again this is the what you call this, the section. Instead of us cutting a section here, what if let us just get a section here at this point? Okay, so if you would be getting the section at that point, let us cut it and let us only consider the beam on the left and erase the right portion of whatever is here. Okay, so if you would now be getting the section here, guys, so again, summation of forces vertical, that is equal to V at A, so the shear at this point or at this section. So from that, guys, so VA is now equal to, so as you can see here, we have 32.111 minus 10 times 4. Okay? So minus 10 times 4, and looking at the calculator, sorry, let me just write it here first. So 10 times 4. This is now equal to, looking at the calculator once again, so 32.1111 minus 10 times 4. Our answer here is negative 7.8889, which we already have a spoiler actually here. So suppose that that is now or let's say that this point here is negative 7.889, since we have our uniformly distributed load here, you would now be tracing it in that manner. So this is now the, what you call this? This is now the shear diagram at this particular section. Okay, so suppose that you want to know the location at this point, just for example. So suppose once again that you want to get the location of this. So let's say that this is X. Okay, so again, summation of forces vertical. So what is the answer at this point? What is the shear here? What is the value of VA or of V at this portion? So that is now equal to 0. Okay, so suppose that you would be cutting once again a section here. So meaning, rewriting our equation, what is now the shear force? So let me just go back to our previous slide. So suppose that this was our section. And you want to know what is the location if V is equal to 0. So meaning, let's say that the shear here is exactly equal to 0. Okay? So that is summation of forces vertical is equal to 0. So from that point, guys, so if this is 32.111, so 32.1111 positive, since it is upward, we would be subtracting 10 kilonewton per meter times what? Times x, because you are solving for it here. So times x, and the answer here must be equal to 0, because once again, you are solving for, where was that again? So we are solving for, well, I actually forgot where we are. So we are actually solving for this value if you want. Okay, so where was that again? So solving for this, x is now equal to, so 32.1111 minus 10 alpha x. So this is now equal to 0. So using shift solve, the answer here is 3.211. Okay, so what that means is that at this portion, meaning that the location of this point where V is equal to 0, it is located 3.211 meters from this support, if ever you want to know about that. Okay, so next up, how do we solve for the next segments? Okay, so let us now proceed to, or let us now get the next point. So at this span, nothing interesting happens. So there are no forces acting at this span. So let us try, guys, to cut a section at the 15 kilonewton force here. However, guys, let us move that section, let's say a microscopic distance to the left of 15. So maybe let's say 0.000000001 millimeters to the left a bit of 15 kilonewtons. So again, as you can see here, guys, we have cut a section a little bit to the left of 15. So meaning 15 would not be included. Okay? So with that being said, guys, this is now the section. Again, we will not include 15 in this analysis because our cut section is a little bit to the left of it. So getting the summation of forces vertical. So summation forces vertical, that is equal to V. Maybe I think it is better if you would be rewriting this value into another entity. Or, okay, so since I have already written it, so let us assume that that is still VA here. So from that, guys, VA is now equal to, so what are the vertical forces acting here? So we have 32.111 minus, so 10 kilonewton per meter times 4. So minus 10 times 4. So do we still have more? So once again, 15 is not yet included because our section is a little bit to the left of 15 kilonewtons. So our answer here is basically, so looking at the calculator once again, so 32.1111 minus 10 times 4. So it is still 7.8889, which is still this answer. So what would just happen is that you would still be plotting the same value. So it just moved horizontally. Okay? So right now, guys, let us now cut a section a little bit to the right of the 15 kilonewton force. Okay? So a little bit to the right, so let's say a micros or let's say a strand of a hair distance to the right just by a bit. So with that, guys, 15 kilonewtons would now be included. So from that, at that portion, guys, let us now solve for the summation of forces vertical once again. This is equal to whatever that force is. So what are the forces that are acting upon it? So we have 32.111 positive minus, so 10 kilonewton per meter times 4 minus 15, since 15 is downward, so minus 15. So with that, guys, this would now be equal to, so negative 7.8889 minus, sorry, that is, once again, 32.1111 minus 10 times 4 minus 15. So our answer here is 22.8889. So meaning, guys, at that location, so at this portion, guys, we will now be plotting. What is our answer? Negative 22.88889. So that is now this value, negative 22.8889. Okay, so that is now our shear diagram up until this portion. So next up, let us return the original beam and let us now cut a little bit to the left of the support. Okay, so if you would be cutting a little bit left to the support, I mean from the support, meaning that the support will not be considered yet. Okay, so with that, guys, let us cut it at that section. And once again, summation of forces vertical. So this is now equal to 32.1111 kilonewtons minus, so this force here, so that is now 10 times 4. What else is being considered? So we have here the 15 kilonewton force. So minus 15 kilonewtons. And looking at, guys, or looking at our calculator, that is the exact same location. I mean, exact same equation, I should say. So just look at the calculator below me and the equation that I have indicated there. It is exactly the same. So meaning, guys, this is still negative 22.8889. And from that, guys, if you would be plotting the shear here, it is still the same. So meaning, guys, that it has just moved to the right horizontally. Okay. So what about if you would be cutting a section a little bit to the right of the this particular support? Oops, what happened? I'm sorry. So we have a spoiler here of 18 kilonewtons. I'm sorry. So that was not supposed to happen. Anyway, so where did this 18 kilonewton force came from? So let us now cut a section a little bit to the right of RB in such a way that in our analysis, RB will now be included. So from that, guys, summation of forces vertical once again, this now equal to, so again, from left to right, so that is 32.1111 kilonewtons minus 10 times 4 minus 15. What else? We now have this 40.8889. So, and since it is acting vertically upwards, this must be plus 40.8889. Okay, so with that, guys, looking at our calculator, so 32.11 or 1111 minus 10 times 4, sorry, minus 10 times 4 minus 15 plus 40.8889. The answer here is 18. Okay, so this is now 18 here, 18 kilonewtons. Okay, so next up, so since we already have that, we are now down to our last span. So what happened here? So there should be a line here. Don't know what happened. Anyway, so let me just, oh, there we go. Okay, so again, guys, we are now down to our last span. Okay, so let us just cut a section at the cornermost. So at the cornermost here, so from that, guys, if you are to cut a section there, including everything, so let me just write it at the bottom part. So the summation of forces, vertical, at this point, guys. So that is now uh, 32.1111, that is this value, minus 10 times 4 once again, minus 15 plus 40.8889 minus 12 times 3 divided by 2, or this area, or the area of the whole triangle. So looking at the calculator once again. Oops, sorry, let me just write it here first. So that is 1 half times 12 times 3. Okay, so looking at the calculator to your left. So 32.1111 minus 10 times 4 minus 15 plus 40.8889 minus zero point 0.5, or 1 half of 12 times 3. The answer here is exactly 0. So meaning at the edge of the beam, the moment here is exactly 0. Okay? So what about for this span? How would we trace it? So if you are thinking that you would just trace it in a very straight line, then I'm afraid that you are wrong. So unlike in here that we have just what do you call this? We have just um traced it in a straight line. This time it wouldn't be the case. Okay, so at this portion, guys, once again, it is not a straight line. Why? Because the load here is varying. So it is not actually a straight line if you would be plotting it. If you would, let's say, cutting a section here, cutting a section per element here, you would not result to a straight graph. Rather, it is now curved. Okay? So the next issue here, once again, it is curved. Okay? So the next thing is that we do not know yet what is the direction of the curve. Meaning, I'm not sure if the curve will now be like this, or if the curve will be like this. Okay, so I'm not sure if it is a crest curve or a sag curve. Okay, so in order for you to know the direction of the curve, you will now be basing it from this load. So at this point, guys, we have a 0 kilonewton per meter load at this point. And it now varies up until this point, whereas at this point, this is now 12 kilonewton per meter. Again, this is 0 and this is 12. Okay, so that is actually, these points here is actually the indication of the slope at these portions. So a little bit of a review when we say slope, that is basically vertical over horizontal, I should say, or rise over run. Okay? So at this portion, guys, the slope there is equal to 0. When we say slope is equal to 0, it means if this is equal to 0, then meaning that y must be 0. So if y is equal to 0, in a given slope, so suppose that we have this line, if it is perfectly horizontal, guys, it means that the slope is 0. But looking at the equation, if y over x is, let's say, equal to, if let's say x is equal to 0, any number divided by 0 will now give you an answer of an infinite answer. And when we say that we have an infinite slope, meaning that it is a vertical line. Okay? So the higher the value of the slope, the more vertical it is. And the less the value of the slope, the more it is horizontal. And if the slope is perfectly equal to 0, it means it is perfectly horizontal. So at this point, guys, once again, the value of the load here is equal to 0. So meaning, guys, that in our curve, the tangent line that we will be drawing here is perfectly equal to 0, or the slope is perfectly equal to 0, meaning that it is horizontal. Then since at this portion here, it is not 0 and it is actually 12, meaning, guys, and since it is pointing downwards, it means that the at the point here, it is actually kind of near vertical. So it, or the tangent line must, must be like that. It is not zero, it is not horizontal, but it is, let's say, near vertical. Okay? So with that, guys, you would be tracing that in such a way that it would now look up, sorry. So let me just erase that. Why can't I erase it? Okay, anyway. So again, let's say that this is the horizontal tangent line. You would now be tracing it in such a way that those are the tangent lines. So this is not really a good drawing. So let me try that again, guys. Let me try that again. So suppose that we have a horizontal tangent line, and let's say a tangent line that is not horizontal but rather downward. So the curve would now kind of look like that. So it is a crest curve. Okay. So this is what you would be calling a 1 degree line, and this is now what you would be calling a second degree curve. Okay. So again, this is not a straight line. It is now curved, and it is now curved in this particular manner. Okay. So in a situation we're in, suppose that your load is, let's say, like this, whereas it is reversed. For suppose that this is now your curve. For its shear diagram, guys, let's say that these are your still your values. Whenever you are to plot it, it would now look like this. So suppose that this is the first point and this is the second point. As you can see, guys, that the zero line is at this point. So meaning that the tangent line at this point is horizontal. And at this point, since this is not zero, this is kind of vertical. So from a vertical tangent line to a horizontal tangent line, meaning that it would first go almost downwards, almost, and it will now proceed to become horizontal. So as you can see here, guys, do you see the difference? So this is, if this is your load, the curve will now be looking like this, and if this is the load, the curve will now look like this. As you can see that they are opposite. Okay, so that is now our shear diagram.